What began as a relatively ordinary weather disturbance over warm ocean waters has rapidly transformed into a storm commanding the full attention of meteorologists, emergency planners, and coastal communities. Just days ago, weather models showed a developing system with only modest potential for strengthening. Similar disturbances form every year, and many never become major threats. Some encounter unfavorable atmospheric conditions that tear them apart before they can fully organize. Others move over cooler waters and gradually weaken. At first glance, this system appeared no different. Yet, as forecasters monitored its progress, a series of changes began unfolding that quickly raised concerns. Satellite imagery showed increasing organization. Thunderstorm activity intensified around the center of circulation. Atmospheric conditions became unusually favorable. One by one, the ingredients necessary for rapid intensification started coming together. Meteorologists first noticed that the storm was developing a more defined structure than originally expected. Large clusters of thunderstorms began wrapping around the center, creating curved cloud bands visible from space. This type of organization is often one of the earliest signs that a tropical system is becoming more efficient. As warm, moist air rises within thunderstorms, energy is released into the atmosphere. That energy helps strengthen the storm's circulation. When the process continues uninterrupted for an extended period, storms can intensify quickly. In this case, weather experts observed exactly that pattern. Each new satellite image revealed a system that appeared stronger and more organized than it had only hours earlier. One of the primary reasons for the storm's rapid development was the exceptionally warm ocean water beneath it. Tropical cyclones derive their energy from warm seas. The higher the water temperature, the more moisture and heat become available to fuel thunderstorm growth. Measurements across the region showed ocean temperatures well above the minimum threshold required to support tropical development. More importantly, the warmth extended deep below the surface. This meant the storm could continue drawing energy from the ocean without significantly cooling the waters beneath it. Such conditions often create an environment highly favorable for intensification. At the same time, another critical factor was working in the storm's favor. Meteorologists closely monitor a phenomenon known as vertical wind shear. This refers to changes in wind speed and direction at different altitudes in the atmosphere. Strong wind shear can weaken storms by disrupting their internal structure and displacing thunderstorms away from the center. Weak wind shear allows storms to maintain organization and strengthen more efficiently. Analysis of atmospheric conditions showed remarkably low wind shear across the storm's projected path. This removed one of the most common obstacles that might otherwise have limited development. As the storm continued organizing, forecasters became increasingly concerned about the possibility of rapid intensification. Rapid intensification occurs when a tropical cyclone strengthens at an unusually fast rate within a short period. This process remains one of the most challenging aspects of weather forecasting because it can dramatically change a storm's threat level in a matter of hours. Communities that initially expect a moderate storm may suddenly find themselves facing a much more dangerous system. While forecasting technology has improved significantly in recent decades, rapid intensification remains difficult to predict with perfect accuracy. Aircraft reconnaissance missions provided valuable insights into what was happening inside the storm. Specially equipped aircraft flew directly through the system, collecting data unavailable from satellites alone. Instruments measured wind speeds, pressure levels, humidity, and temperature throughout the storm's structure. The results revealed a strengthening circulation and falling central pressure. These findings confirmed what meteorologists had suspected from satellite observations. The storm was not only organizing visually, but was also becoming stronger internally. Pressure changes within a tropical cyclone often provide important clues about future development. Lower pressure at the center generally indicates a stronger storm. During several observation periods, meteorologists recorded significant pressure drops over relatively short timeframes. Such declines frequently signal that intensification is underway. Combined with strengthening winds and increasing thunderstorm activity, the pressure trends suggested that the storm's development was accelerating rather than slowing down. Satellite imagery became increasingly dramatic as the system evolved. Infrared sensors detected extremely cold cloud tops around the center, indicating powerful thunderstorm growth. Visible imagery showed cloud bands wrapping tightly around the circulation. In some observations, meteorologists identified signs of an emerging central dense overcast, a feature commonly associated with strengthening tropical systems. These visual indicators reinforced growing concerns among forecasting agencies. The storm's expanding size also attracted attention. While peak wind speeds often receive the most public focus, storm size plays a major role in determining overall impact. Larger storms can affect wider areas with strong winds, heavy rainfall, dangerous surf, and coastal flooding. As the circulation expanded, meteorologists noted that hazardous conditions could eventually extend far from the center. This increased the potential area of impact and complicated preparedness efforts for regions along the projected path. Heavy rainfall quickly emerged as one of the most significant concerns. Tropical cyclones are capable of transporting vast quantities of moisture through the atmosphere. When this moisture condenses into rain, the resulting precipitation can be extraordinary. Forecast models indicated the possibility of prolonged periods of heavy rainfall in areas affected by the storm. Rivers, streams, and urban drainage systems could face significant stress if rainfall accumulations reach projected levels. History has repeatedly shown that flooding often becomes one of the most destructive consequences of tropical cyclones, sometimes causing greater damage than wind itself. Storm surge represented another major hazard. As powerful winds push ocean water toward shore, coastal water levels can rise dramatically above normal tides. This process can flood roads, homes, businesses, and critical infrastructure. Storm surge danger often increases rapidly as a storm strengthens because stronger winds exert greater force on the ocean surface. Emergency management officials carefully monitored updated surge projections as intensity forecasts continued rising. Even small increases in wind speed can translate into significant increases in surge potential for vulnerable coastal communities. Meteorologists also paid close attention to the storm's environment beyond immediate atmospheric conditions. Large-scale weather patterns influence both movement and intensity. High-pressure systems, troughs, and steering currents determine where tropical cyclones travel. Forecast models suggested that the storm would remain within a generally favorable environment for at least the near future. This increased confidence that strengthening could continue before any significant weakening factors emerged. Public interest in the storm expanded rapidly as forecasts became more concerning. News organizations provided frequent updates. Weather enthusiasts monitored satellite loops around the clock. Residents in potentially affected regions began reviewing emergency plans and gathering supplies. Emergency management agencies emphasized the importance of preparation, particularly because rapidly intensifying storms can leave limited time for last-minute actions. Officials encouraged communities to focus on readiness rather than waiting for complete certainty regarding the storm's exact path. One challenge associated with rapidly intensifying storms is that forecast changes can occur quickly. A slight adjustment in atmospheric conditions may significantly alter future intensity projections. For this reason, meteorologists continuously update forecasts as new observations become available. Every aircraft reconnaissance mission, satellite pass, ocean measurement, and weather model run contributes additional information that helps refine predictions. The forecasting process remains dynamic, especially when dealing with systems undergoing rapid change. Ocean heat content continued supporting concerns about additional strengthening. Scientists measuring conditions beneath the surface found substantial reservoirs of warm water extending to significant depths. This factor is particularly important because strong storms often churn the upper ocean, bringing cooler water to the surface. When warm water extends deeper below the surface, the storm is less likely to weaken itself through this mixing process. Instead, it can continue accessing large amounts of energy as long as other atmospheric conditions remain favorable. By the latest observation period, there was little doubt among experts that the storm had entered a dangerous phase. What had once appeared to be a relatively ordinary weather system was now displaying many of the characteristics associated with major tropical cyclones. The circulation had strengthened, thunderstorm activity had intensified, pressure levels had fallen. Environmental conditions remained supportive. Forecast confidence regarding continued development was increasing. Emergency planners understood that every hour of additional strengthening could significantly affect potential impacts for communities along the storm's projected path. As meteorologists continued analyzing incoming data, one message became increasingly clear. This powerful storm was intensifying rapidly. The atmosphere was providing support. The ocean was supplying energy. Structural organization was improving. Forecast models continued indicating the potential for additional strengthening. While uncertainty always remains part of tropical cyclone forecasting, the overall trend was undeniable. The storm was becoming more dangerous with each passing update, and weather experts were watching closely to determine just how powerful it might become before its next phase began. As the storm continued intensifying, meteorologists began observing signs that its internal structure was becoming increasingly efficient. This was not simply a case of stronger winds or larger thunderstorm clusters. The storm itself was evolving into a more organized and powerful system capable of sustaining rapid development. Satellite imagery revealed dense bands of thunderstorms wrapping tightly around the center. Areas that had once appeared disorganized were now showing clear signs of rotational symmetry. For weather experts, this type of structural improvement often signals that a storm is entering one of its most dangerous stages. Aircraft reconnaissance missions provided some of the most important information during this period. Pilots flying directly into the storm encountered stronger winds and lower pressure with each successive mission. Instruments released into the atmosphere transmitted detailed measurements back to forecasting centers, allowing meteorologists to build a clearer picture of conditions inside the cyclone. Several reports indicated that the storm's core was consolidating and becoming more stable. This development was particularly concerning because a stable core allows a storm to convert ocean heat into atmospheric energy with greater efficiency. One of the defining characteristics of rapidly intensifying storms is the formation of a strong central circulation surrounded by persistent thunderstorm activity. Meteorologists noted that the storm's thunderstorms were no longer scattered randomly throughout the system. Instead, they were concentrating near the center, creating a powerful engine capable of sustaining further strengthening. Infrared satellite imagery revealed extremely cold cloud top temperatures, indicating intense upward motion within the storm. Such observations suggested that large amounts of heat were being released into the atmosphere, fueling continued growth. At the same time, ocean conditions remained exceptionally favorable. Sea surface temperatures across the storm's projected path continued providing an abundant energy source. More importantly, ocean heat content measurements showed that warm water extended well below the surface. This meant that even as the storm churned the ocean beneath it, cooler water would not immediately reach the surface in sufficient quantities to weaken the system. This deep reservoir of warm water effectively acted as a continuous fuel supply, allowing the storm to maintain its strengthening trend. Meteorologists also examined atmospheric moisture surrounding the cyclone. Dry air can often disrupt tropical systems by weakening thunderstorms and interfering with internal circulation. In this case, however, the environment remained remarkably moist. High humidity levels surrounded the storm across multiple layers of the atmosphere. This reduced the likelihood of dry air intrusion and allowed thunderstorm development to continue largely uninterrupted. Combined with low wind shear and warm ocean temperatures, the moisture-rich environment created nearly ideal conditions for tropical intensification. As forecast models incorporated new observations, many began projecting stronger intensity outcomes. While differences remained regarding exact wind speeds and timing, the overall trend was consistent across numerous forecasting systems. Nearly every model indicated continued strengthening over the coming period. Such agreement among forecasting tools often increases confidence among meteorologists, particularly when supported by direct observations from aircraft and satellites. Emergency management agencies closely monitored these updates because even small increases in projected intensity can significantly affect preparedness decisions. Public attention intensified alongside the storm itself. News coverage expanded as forecasters issued increasingly urgent updates. Coastal residents followed forecast tracks closely, hoping to determine whether their communities might eventually face direct impacts. Social media platforms filled with satellite images, forecast maps, and weather discussions. While public interest often focuses on the exact projected path, meteorologists repeatedly emphasize that dangerous weather extends far beyond the center of a storm. Heavy rain, rough surf, strong winds, and coastal flooding can affect regions located hundreds of kilometers from the point of closest approach. Rainfall forecasts became increasingly concerning. Tropical cyclones possess the ability to transport enormous quantities of atmospheric moisture. As the storm strengthened, its capacity to generate heavy rainfall also increased. Some forecast scenarios suggested prolonged periods of intense precipitation over affected areas. Such rainfall could quickly overwhelm drainage systems, flood low-lying regions, and cause rivers and streams to rise rapidly. Flooding often persists long after winds begin to weaken, making it one of the most dangerous aspects of tropical weather systems. Storm surge projections also continued increasing. As wind speeds strengthened, forecasters adjusted surge estimates accordingly. Coastal flooding poses unique dangers because water can advance inland rapidly, affecting areas that may not appear vulnerable during normal conditions. Roads become impassable. Critical infrastructure can suffer significant damage. Evacuation routes may be compromised if preparations are delayed. Emergency officials stress that surge danger should be taken seriously because it has historically caused some of the most severe impacts associated with major tropical cyclones. Another concern involved the possibility of tornado development. Tropical cyclones occasionally produce tornadoes within their outer rain bands, particularly as they approach land. While these tornadoes are often smaller than those associated with major severe weather outbreaks, they can still cause significant damage. Forecasters monitored atmospheric conditions for signs that tornado-producing environments might develop in areas affected by the storm's outer circulation. This added another layer of complexity to an already challenging forecast situation. The aviation and maritime sectors also faced growing challenges. Airlines reviewed flight schedules and contingency plans as the storm expanded. Airports in potentially affected regions prepared for operational disruptions. Shipping companies monitored forecast updates and adjusted routes to avoid dangerous conditions. Ports evaluated procedures for securing equipment, protecting facilities, and ensuring safety for personnel. The influence of a major tropical cyclone extends well beyond immediate coastal impacts, affecting transportation networks across large geographic regions. As the storm's circulation strengthened, ocean waves generated by the system began spreading outward across vast distances. Long before the storm itself approached land, dangerous surf conditions developed along some coastlines. Large waves increased the risk of coastal erosion, rip currents, and hazardous marine conditions. Beachgoers, boaters, and coastal residents were advised to remain cautious as ocean conditions deteriorated. These impacts served as an early reminder that the storm's influence was already being felt despite remaining far from many populated areas. Meteorologists remained particularly focused on the possibility of continued rapid intensification. Historical records show that some of the most destructive storms undergo dramatic strengthening shortly before affecting land. Advances in forecasting have improved the ability to identify favorable environments, but predicting the exact timing and magnitude of rapid intensification remains difficult. Because the current environment continued supporting development, forecasters could not rule out additional periods of significant strengthening. Emergency preparedness efforts accelerated as forecast confidence increased. Local governments reviewed evacuation procedures, emergency shelter operations, communication systems, and resource distribution plans. Utility companies prepared response crews for potential outages. Hospitals evaluated emergency staffing needs. Residents in vulnerable areas gathered supplies and reviewed family emergency plans. Officials consistently emphasized that preparation becomes easier and safer when completed before severe weather conditions arrive. One of the most striking aspects of the storm was the speed with which it had evolved. Only a short time earlier, it had been regarded as a relatively ordinary tropical disturbance. Now it had become a major weather system capable of producing widespread impacts across multiple regions. This transformation highlighted the dynamic nature of tropical cyclones and the importance of continuous monitoring. Conditions that appear manageable one day can change dramatically the next when environmental factors align in favor of intensification. Satellite imagery near the end of the observation period revealed a storm that looked increasingly mature. Cloud patterns displayed strong organization. Thunderstorm activity remained intense. The central circulation appeared well-defined. Forecasters examining these images recognized many of the features commonly associated with powerful tropical cyclones. Combined with aircraft observations and environmental analyses, the visual evidence supported growing concerns about the storm's future strength. As meteorologists prepared the latest forecast updates, the overall message remained clear. The storm was intensifying rapidly and showed few signs of slowing down. Warm ocean waters continued supplying energy. Atmospheric conditions remained favorable. Internal organization was improving. Forecast models supported additional strengthening. Potential hazards including flooding, storm surge, damaging winds, rough surf, and isolated tornadoes all remained significant concerns. While uncertainty persisted regarding exact impacts and locations, the trend itself was unmistakable. This powerful storm had entered a phase of rapid development, and weather experts were closely monitoring every change as it continued evolving into an increasingly dangerous system.